Hi Organickers, welcome back. This is a quick video to give you a little review of proton or hydrogen NMR spectroscopy. I'm going to use ethyl acetate as an example spectrum. We're going to kind of work through that. I'm starting out here on our Moodle page to show you some of the resources you have available for you for proton NMR. Obviously you can look in the book in sections 14.1 to 14.8, your textbook, and read through that to get some review of NMR. I've also put a link to this NMR primer document, which was prepared by Luke and is a really nice overview of a lot of the things we'll be talking about in proton NMR, so another good resource for you. I've also got a couple handouts down here, overview of chemical shifts in proton NMR and introduction to spin-spin coupling in proton NMR. I'll be giving you copies of those in class, so you don't have to make copies yourself right now. And then I have a link to an online organic chemistry online spectroscopy page, which has some practice NMR and some other practice NMR problems down below. What we're going to do today is focus on this introductory proton NMR video, which you're watching right now, and I've put on there the spectra that we'll be looking at, this ethyl acetate spectrum, both the full spectrum and the zoomed in. You might want to load those and print them out in case the screen resolution isn't so good on the video. And then there's another spectrum of this compound with the formula C9H12O. And again, there's a full spectrum and a zoomed in one of those. So again, if you want to pause the video and go at least download those or print them out, it might be helpful for following along. Okay, so let's go and look at a proton NMR. The proton NMR, also sometimes called hydrogen NMR, is, as the name suggests, only going to show hydrogen atoms, and all the hydrogen atoms in the molecule will show up in the proton NMR. Proton NMR is by far the most important form of spectroscopy in organic chemistry, and so learning to become comfortable with it and analyze the spectra is a real important skill. So we're starting out with ethyl acetate. I've shown the structure up here of ethyl acetate. It's a common solvent, so you might actually run into this as a sort of a contaminant in some of your spectra, so it's kind of a good one to become familiar with. And what I thought I'd do is just take us through some of the main parts of the spectra and how to start analyzing it as sort of a review. Again, I assume you've seen all this before, first semester, at least the general outlines, and this is just to kind of get you up to speed. So let's look at the different parts of the spectra. So let's look along the bottom at the scale. This scale is in parts per million, which is sort of an unusual scale. It's actually related to the frequency of the absorption, or conversely to the wavelength, but sort of think of this in terms of frequency along this axis. The reason why it's in parts per million is it's a shift relative to a standard. This little peak right down here at 0 ppm is tetramethylsilane, which is used as a standard. And the reason that we do the parts per million relative to that is we're dividing by the overall frequency of the spectrometer, and that way different spectrometers with different magnetic field strengths will all have their peaks for a given compound come at the same chemical shift. Otherwise, different NMR spectrometers would have their peaks at different frequencies, and so the parts per million scale just normalizes that so I can compare to different spectra taken on different instruments. Okay, just to kind of get us oriented, there's a number of peaks in the spectrum. You can see there's a peaks here, there's a peak right here at around 2 ppm and one up around 4 ppm. There's also some very small peaks, and I just kind of wanted to point those out before we started because you'll sometimes run into those and sometimes students get confused about what those are. So this very little peak at 0 parts per million is our standard tetramethylsilane, and that's often added to the NMR tube so that you can reference to that. In some spectra you might not see that, they might be referenced some other way, but if you see a small peak around 0, that's almost certainly what it is. Now you're most commonly going to see spectra that are acquired in deuterochloroform, which is just chloroform with a deuterium put in. If that was regular chloroform, you'd have a huge signal from that proton, which would kind of swamp out things. And although you could get a good, decent spectra that way, oftentimes people use the deuterochloroform. When you buy the deuterochloroform, however, it's not pure deuterochloroform. There's a little bit of hydrogen in there, usually much less than 1%, maybe 0.1%, but since you're using it as the solvent, that is going to show up. And that little peak right down here at about 7.26 ppm, that's your chloroform peak, little residual chloroform in there. And one other peak that you'll often see in the deuterochloroform spectra is right around 1.6 1 to 1.7 ppm. Small peak can be a little water in there. So if you have a little water, it'll show up there. So those little peaks are things that we're not really concerned with here, but I just wanted to point them out. We're interested in these big peaks, which correspond to our ethyl acetate sample. Now also on the NMR spectra, you see this funny little line here. This is the integration, which is sort of telling you the area under these peaks, and that, it turns out, is directly related to the number of protons, so that's going to be very useful for us. So in this little video, I'm just going to go through the simple analysis of this NMR spectra to kind of get you back up to speed. So when we go to analyze a spectra, I want to kind of give you a standard way of doing it that might be helpful. The first thing to do is to use the integration to determine the distribution of hydrogens in the molecule in the spectrum. How many hydrogens correspond to each peak. Then you can use the chemical shifts where they come in the spectrum to sort of determine things about the chemical environment around the different hydrogens. And finally, you can use the splitting patterns to determine how those hydrogens are arranged relative to each other. So it gives you a very nice way to build up the entire spectra, or the entire molecular structure. So let's go back to our spectrum here, and let's start out then with the first of those things to look at the integration. So here I've got the integration, and on our NMR it already prints out sort of the relative size of these integration peaks. Now if these weren't written there, and commonly they're not, if you find spectra from various sources, you would have to measure the distance from this line right here where it starts up to where it finishes up here, and you'd measure that distance. I would recommend investing in a ruler that has a millimeter scale on it, and I usually just measure these out in millimeters. So although this would be too big, you could imagine that might be 95 millimeters, and that would be 150 millimeters measuring from there to there. So in this case, the NMR has already sort of arbitrarily picked some relative scale and put some numbers on there. Now, what we want to do is we want to think about how those numbers correspond to the number of protons in the molecule. So the first thing we can see is there's 3 different peaks corresponding to 3 different types of protons. And if we look at our ethyl acetate, it's pretty clear what 3 different types we have. We have the hydrogens on the methyl group, we have the hydrogens on this CH2, and we have the hydrogens on this other methyl group. And the first thing we can notice is that this peak is smaller than those 2 peaks. These are about the same height. And by the way, there's often a 5 to even almost 10% error in the NMR spectra. So if things are not perfectly exactly correct when you do the integration, don't worry too much about that. But these are basically the same. We could round them off to say 150, and maybe rounding off again to about 100 here, you can see that these are about 1.5 times as high. Well, what that means is that there's more protons, of course, in these peaks, and of course if we look at the structure here, since we know what the answer is, there's 2 CH3s, so those would obviously be bigger than the CH2, and in fact they'd be bigger in a 3:2 ratio, in other words 1.5 times bigger. So you can see that these peaks are 1.5 bigger than that. Now, if you didn't know what the structure was and you didn't know what this corresponded to, one of the first ways that I usually do is just take the smallest integral in your spectrum and assume it's 1. So if that's 1, then how much would that be? Well, you could find that out by taking this number and divide it by that one. You'd see it's 1.5. And you say, well, wait a minute, I can't have 1.5 hydrogens, so that can't be 1 to 1.5. It must really be, multiply this by 2, 2 to 3. And that starts to make a lot more sense. You say, okay, there's 2 protons there, and 3 there, and 3 there. And so then you say, oh, well, that makes sense to me because I've got 2 protons there, I've got 3 there, and I've got 3 there. So even without doing anything in terms of complex analysis, just from the integration, you can start to sort of see what's going on in the molecule. So what I would recommend is if you have printed out this spectra, is go ahead and just label this right here like 2H, 3H, and 3H. So you know how many hydrogens correspond to each. Now remember, in the NMR, you don't actually know the absolute number, you just know the relative number. So if we didn't know how many total hydrogens there was or what the answer was, this could certainly also be 4 to 6 to 6. Okay, it wouldn't have to be 2 to 3 to 3. But since we're going to normally know how many protons there are total from the molecular formula, or in this case we actually have the structure, we know that it must be 2 to 3 to 3. So that's the first thing you want to do when you look at your NMR. And a lot of times I think students don't spend enough time looking at the integration because it's pretty simple and it gives you a lot of really valuable information. Now what if you had a spectrum, and this occasionally happens, where there's no integration there? Well, then you sort of have to go based on sort of peak height, and that's a little trickier because the peak widths aren't always the same, so then peak height doesn't work that accurately. But just if we were going to take, for an example here, you can see this peak goes all the way up to here, that single peak, and this is broken down into 3 peaks. If you added the size of those peaks together, you'd see that they'd add up almost exactly to the same size as that one. Whereas if you added the heights of these 1, 2, 3, 4 lines here, they wouldn't, they'd be a little bit shorter than that. So that's one way that you can do kind of a crude analysis if there's not an integral on it. But again, you're not going to be able to get the accuracy that you really want. So normally you're going to want to have an integral on your spectrum. Okay, so that was the first thing that we did. If we go back and look, we used the integration to determine the distribution of hydrogens in the spectrum. The second thing you want to do is use the chemical shift to get some information. Now, here we've got something at around 1 ppm, something around 2 ppm, and a peak around 4 ppm. We should know what those correspond to in terms of the chemical environment. Now, the way to go find that is if you look at this Introduction to Chemical Shifts in Proton NMR. I'll click on that and bring it up. You can see here I've tried to summarize on one page, and again I'll hand this out in class, the different chemical shift ranges. So remember, as we said, there was something around 1 ppm, so that's just a normal alkane CH. Then we had something up around 2 ppm. Oh, that means it might be a proton adjacent to an sp2 carbon. So for example, here's a CH3 that's next to an sp2 carbon. So that comes at around 2.14. Here's another one, a CH3 next to an sp2, in this case an alkene versus a carbonyl, comes up about 1.64. But in other words, that could be a clue that that peak that was shifted up around 2 might be next to it. And of course, if we go back and look at that, we'll see that of course there is a CH3 that's next to a carbonyl. So that's sort of confirming that that must be what that CH3 is. The one that's up at 4 ppm, what does that one correspond to? Well, again, if we look at our chemical shift ranges, in the 4 ppm range, that would be adjacent to an electronegative atom. So in our spectrum here, when we go and look, you can see that we have a carbon with hydrogens that's adjacent to an oxygen atom. And those CH2s are getting shifted up because they're next to it. So one of the important things that you need to do for this class is to start to learn these chemical shift ranges. So what I would recommend doing is making flashcards with these different regions on them. So you'd have this region on a flashcard, you'd have this region, and this region, you know, on one side of the flashcard you'd sort of put the range, and on the other side you'd put what it corresponded to, and then you could look at the flashcards and turn them over. A couple really important ones, the alkenes up around 4.5 to 6.5. The aromatic is probably the most distinctive. That's the one that students usually get the best, or right away start to learn to look in that region for aromatic ring protons. Aldehyde protons up in very distinctive range around 10 ppm, and carboxylic acids can be up even further. Hydrogens that are attached to oxygen and nitrogen and alcohols and amines typically come variable 1 to 5 ppm. That'll depend on what solvent's being used, the concentration, etc. They're oftentimes also slightly broad. Now the one last thing I want to mention about chemical shifts is, although I've given you sort of these simple little regions to learn, chemical shift effects are additive. So if you had something that was next to 2 electronegative atoms, it might come up further than 4.5. So for example, if we have dichloromethane, which has a carbon with 2 chlorines on it, those hydrogens come up at like 5.2 ppm. And as we saw before, in chloroform, right up here around 7.26, that's a hydrogen that's on a carbon with 3 chlorines next to it. So that would normally be considered the aromatic range. but it's just been shifted up there by having multiple groups. So this can sometimes complicate it, but those simple regions that are on that handout give you a good starting point in starting to think about the spectra. So again, if we looked at the shifts, we could automatically, and knew what the structure was, we could say, well, this one's furthest down because it's on a CH3 next to a normal sp3 carbon. This one is shifted up a little further because it's next to an sp2. And finally, the one that's shifted all the way up are the hydrogens on the carbon that are next to the oxygen. So the electron withdrawing group helps to remove electron density away from those hydrogens, and that has the effect of shifting the chemical shift up. It's said that it's more de-shielded. Okay, so there we go. We've done the first two of our little little things here. We've used the integration, we've used the chemical shifts. Finally, let's talk a little bit about the splitting patterns. The splitting patterns are the ones that I think give students the most trouble in analyzing the proton NMR. We'll spend a lot of time in class talking about those, but I kind of wanted to look at those splitting patterns. So when you have hydrogens that are neighboring to other hydrogens, but that aren't equivalent, that is, that are not the same as the other hydrogen or have the same chemical shift, they don't split each other. So this CH3 right here, it has the 3 hydrogens on this carbon, but since they're all equivalent, they don't split each other. And on the adjacent carbon here, there's no hydrogens there, so there's no splitting, so that ends up coming as a singlet. Whereas this terminal CH3 on the end right here, it has 2 hydrogens on the adjacent carbon. Those are neighboring to it, and when we say neighboring, we're talking about 2 to 3 bonds away, so these would be 3 bonds away. And so these hydrogens cause their neighbors to be split into characteristic patterns, and again, I assume you've seen this before last semester, and we'll talk about it more. But one of the simple things we learned is that if you have a CH3 and you have 2 neighbors that are equivalent, that'll split it into 3 peaks. That's sometimes known as the n+1 rule, where you have 2 neighbors and you add 1 to the 2, you get 3. That's your n+1, and so you have 3 peaks, and here they are 1, 2, 3, otherwise known as a triplet. The CH2, by contrast, has 3 neighbors, so that means it gets split into 4 peaks, or what we might call a quartet. So 1, 2, 3, 4. So that's the kind of splitting patterns that you normally see. They start small, they get big, and they go down, and you have those n+1 sort of peaks. Now, as we'll see later when we look at other spectra, if the neighbors aren't equivalent, then the splitting patterns can be a little bit different. But this is enough to kind of get us going here. Now, again, if you want to think about more about splitting patterns, I've got a handout on the Moodle page, and again, I'm going to hand this out. Oops, sorry about that. Computer's asking me for lots of questions here. If you go and look at this introduction to spin-spin coupling in proton NMR, that handout sort of shows you the different splitting patterns. So for example, here it would be a single peak where it didn't have any neighbors. Then if it had 1 neighbor, it would get split into a doublet. If it got 2 neighbors, like we saw with that CH3 group, it gets split into 3, 1 to 2 to 1, that's our triplet. Or if there were 3 equivalent neighbors, it would get split into a quartet that we saw before. If we have non-equivalent splitting, as I mentioned, we'd initially get a doublet again, but now when it's split, the 2 middle peaks wouldn't overlap, and so we'd have 4 peaks, and that would be called a double doublet. But they'd all be the same size instead of like the quartet where they start small and get big. So again, we'll look at that. We'll also look a little bit at the magnitude of the coupling constants. I'm not going to worry about that right now in this introduction, but this is a handout that you'll want to take a look at, and we'll go through in class. Okay, so let's go back. We've now done sort of our full analysis of the spectrum where we've seen the splitting patterns, we've seen the chemical shifts, and we've seen the integration and used that to assign all of the protons in this molecule. And again, when you do a hydrogen NMR, all the hydrogens in the molecule have to show up somewhere in the NMR spectrum. Okay, so now what I'd like you to do to prepare for class is to look at this next spectrum, which is of a molecule where I've given you the formula C9H12O. And this is typically the way that you'll see a problem like on a quiz and exam, where you might be given a formula, you're given a spectra with an integration, and your job is to try to figure out what that compound is. So how are you going to do that? Well, you're going to go through the 3 steps we've talked about before. You're going to use integration to determine the distribution of hydrogens, then use chemical shifts to determine the chemical environment around the different hydrogens, and then use splitting patterns to determine the relative location. And from that data, hopefully you'll be able to construct the whole structure of the molecule. Now, when you're doing this, one of the most important things to do is to actually write down sort of chemical structures as you start to do them. So we'll go through that in class, but just to kind of get you started here, the first thing you would want to do is look at these integrations. Now, I purposely removed the numbers here because a lot of times in books and in different spectral databases, they won't show the numbers. So you'll have to actually get your ruler and measure these yourself. So I'm going to leave that for you to do and figure out what the ratio is. And then in a problem like this, you're told that there are 12 total hydrogens. So once you take these integrations and start to break them out, you'll want to make sure that they add up to a total of 12 hydrogens. So that'll be one job. So get these integrals, right numbers, you'll get the relative amounts, and then try to figure out how many hydrogens are in each part of the spectrum. The next thing you'll want to do is use the chemical shift ranges to give you some information. So some of these peaks, obviously this one's coming up, this one's coming way up. So by using that little handout on chemical shift ranges, and eventually you should just be able to do that from your own experience, you'll be able to assign some of these peaks to certain environments. In some cases you won't know necessarily what they are, but you get some clues from that. And finally, the last thing that you'll do is you'll look at the splitting patterns, and I've actually done a zoom in of this so that you can see it a little better. So here is a zoom in of the region from about 4 ppm down to 1.5 ppm so that you can look at those a little closer. So here you see a nice pattern, here's another nice pattern, here's another one. But what I want to point out is notice that this is sort of 2 different patterns that are just close together. And so I'll just give you a little hint here. That'll often happen. I mean, there's a finite amount of spaces for protons to come, and sometimes they'll just come on top of each other. So when you look at this, if you see a nice pattern like this, you can say, okay, that's probably one type of proton. But when you see something that's more complicated, where you have sort of a nice pattern here, but then you've got another one that's non-symmetrical relative to this, you say, oh, well, maybe that's just another proton on there of a different type. So what I want you to do now is take a stab at this. Go through those different steps, see if you can figure out what the structure of that molecule is. And that's kind of our first little practice at doing NMR. So tomorrow in class we'll talk about this in more detail and look at some other examples, but if you can kind of get up to speed on this first sort of simple analysis, you'll be well on your way to starting to understand proton NMR. Okay, that's it.